Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying methods of differentiation lecture 2. This is our QOD 21. Let's take the screenshot and here we go. So in our differentiability lecture 3 probably I think we studied about inverse trigonometric functions and their derivatives. So basically we just memorized these derivatives but we didn't know how did we derive them. So let's take a look how can we derive these inverse trigonometric functions derivatives. So let's take one example of sine inverse x. So we have a function y equals to sine inverse x. Now we know that with the basic methods we know about differentiation, we cannot really find out the differentiation of inverse trigonometric functions. So basically we'll have to do some kind of substitutions. So with that I'll be introducing substitution method. So let's take one example over here. The obvious substitution over here would be x equals to sine theta. Now when I put it over here, I will get y equals to sine inverse sine theta. That would be theta only, right? So if I write dy by dx, that would give me d theta by dx. Now we have to find out this value. This value we can get from over here. So x equals to sine theta, taking dx by d, differentiating it with respect to theta, we'll get cos theta. So basically d theta by dx would be 1 by cos theta. Now we have to write cos theta in terms of x. Now we know that x square equals to sine square equals to 1 minus cos square. So basically cos theta would be under root 1 minus x square. So that would give me 1 upon under root 1 minus x square. So this value basically is this only. So this is the basic derivation using a method of substitution. So now let's look at some standard substitutions. Our main motive to do substitutions is to make it simpler, may simplify the statements or expressions which we have been given. So over here we don't really like to differentiate terms inside under root. So that's why we have to remove the under root. So for that what I'll be doing, I'll be replacing x with a sine theta. If it was 1 over there, then I'll just do sine theta or cos theta. That would remove this entire root expression. Similarly over here, if I use x as a tan theta or a cot theta, our under root will be removed and we'll get a simpler expression. So our main motive is to simplify things and after that we can differentiate it. So these are the standard substitutions which you will be using in both differential and integral calculus. Now let's take one example. Y equals to tan inverse under root 1 plus x square minus 1 divided by x, and we have to find the differentiation of it. Now we can clearly see that if I just put x equals to tan theta over here, then I'll get rid of this under root part, right? So I'll use x equals to tan theta. So that would reduce this expression into y equals to tan inverse. That would give me sec theta minus 1 divided by tan theta. That would give me tan inverse. I'll just write it in forms of sine and cos. That would give me 1 minus cos theta divided by sine theta. Now, still it's not in a simpler form. So that's why what I'll be doing, I'll be converting into this half angles. So 1 minus cos theta is 2 sine square theta. That would give me tan inverse 2 sine square theta by 2 divided by 2 sine theta by 2 cos theta by 2. So this gets cancelled out and the expression becomes tan theta by 2, which is basically theta by 2. Now we have got y equals to theta by 2, and there is one probable mistake which anyone can do. So when we have done the substitution x equals to tan theta, so basically we have to find dy by dx at x equals to 1, right? So what people will do, okay, since we have done the substitution, so basically we have to find, they'll assume that they have to find dy by theta at x equals to pi by 4. And it seems obvious, right? Because dy by dx at x equals to 1, that means dy by d theta at pi by 4. So they'll just differentiate it, dy by d theta, that would come out to be 1 by 2. But that's not correct. Let me tell you why. Because if they have asked you dy by dx in the question, then you have to convert this into the other formats. So basically what I'll be doing, I'll be writing it as dy by d theta into d theta by dx. Now this is the actual expression which we have to calculate and not just dy by d theta. This is just a part of dy by dx. So just remember that, don't do this in the examination and you'll get the answer 1 by 2. If you do this, then you'll get answer as 1 by 4. So you will get d theta by dx using this expression, and dy by the d theta is 1 by 2, and you will get eventually 1 by 4. So just remember that this kind of mistakes can happen. Now let's talk about parametric differentiation. So what happens is sometimes they'll be giving you x and y in terms of another parameter. Let's say we have been given x equals to sine theta and y equals to cos theta, but they ask dy by dx. Now many people think why this format is working. We have to calculate dy by dx, and which will eventually be written as dy by d theta into d theta by dx. This is how it's going to be written. But why are we doing that? Because, sorry, let's look at the derivation part. We know that dy by dx is nothing but limit uh, both delta y and delta x tends to 0, delta y by delta x. This was the original thought for derivatives, right? For the differentiation. So that's why we are able to cancel these terms out. If we are doing successive differentiation, then we might not be able to cancel out them directly. So as of now, it's linear. That's why we are able to cancel out, and we are able to write it in format. But once we include higher order derivatives, then we won't be able to do that. So just because we can write it like this, don't try to apply this in the higher order derivatives. But in case of linear format, single derivation, single order derivative, then you can write it in this format, and that is how we are going to do parametric differentiation. So let's look at it with the help of one example. Find dy by dx is if x equals to a theta minus sine theta and y equals to a 1 minus cos theta. So x equals to a theta minus sine theta, y equals to a 1 minus cos theta. Now I'll be doing dy by dx equals to dy by d theta into d theta by dx. I'll just take it towards in the denominator. So that would give me dy by d theta divided by dx by d theta. So dy by d theta would be a times 1 minus cos theta, and dx by d theta would be a times sine theta, right? Now you just have to divide it. That would give me a times 1 minus cos theta divided by a times sine theta. A gets cancelled out. 1 minus cos theta is 2 sine square theta by 2 divided by sine theta is 2 sine theta by 2 dot cos theta by 2. This gets cancelled out and you'll eventually get tan theta by 2 as the answer. So this is the answer, right? So I had another page over here. I'll just write it once again. So basically we got 1 minus cos a times 1 minus cos theta dy by dx divided by a times sine theta. That would give me 2 sine square theta by 2 divided by 2 sine theta by 2 dot cos theta by 2. That would eventually become tan theta by 2. Now you also know that why we have taught trigonometry first, because trigonometry is also going to be highly used in all sorts of calculus problems, be it functions, limits, continuity, differentiability, integrals, anything. So that's why you should also remember these trigonometric identities. Now let's study one more similar kind of concept, differentiation of one function with respect to another function. So let's say you are given one function u equals to fx and v equals to gx. Now what you have to do, you have to find du by dv. Again, we can do the same adjustment. We can find du by dx multiplied by dx by dv, and mind that we are doing it just for the first order derivative and not for the higher derivatives. And that would eventually give me du by dx whole divided by dv by dx. So basically you have to differentiate the u function with respect to x, you have to differentiate v function with respect to x and divide them. So that is just similar to the parametric differentiation. So now let's look at this example. We have been given one function y equals to tan inverse under root 1 plus x square minus 1 divided by x. Now we know that if we just want to differentiate it directly with respect to tan inverse x, it would be very difficult. And even if we are just going to differentiate it with respect to x, And also it's going to involve inverse function, quotient rule, chain rule, etc. So it's not a good thing to start with the basic rules of differentiation. So what we'll be doing substitution over here. So x equals to tan theta is the obvious substitution. So basically so we'll be getting dx by d theta equals to sec square theta, and that would give me 1 plus x square. Now we have to find dy by d tan inverse x. Now I'll just replace it with dy by dx divided by d tan inverse x divided by dx. Now in the example we did few minutes back, we saw that this comes out to be y equals to theta by 2, right? So dy by d theta, that would be 1 by 2, and d theta by dx equals to 1 plus x square from here. So if I multiply both of them, I'll be getting dy by dx equals to 1 by 2 times, sorry, 1 by 2 times 1 plus x square. So I'll be plugging this value over here. What I'll be getting? 1 by 2 times 1 plus x square divided by d by dx of tan inverse x, that is also 1 by 1 plus x square. So that would eventually give me 1 by 2 times 1 plus x square whole square. So this would be the final answer. Now successive differentiation is not that big a part of PGDBA syllabus. So what I'll be doing, I'll be just touching upon the few things. So basically what happens is, let's say we have been given one function y equals to, let's say, sine x. Now if I'm doing dy by dx, I'll be getting cos x. If I differentiate this function once again, so I'll be doing d2y by dx square, I'll be getting minus sine x. So basically this is the first order, this is the second order, and we can do it for higher orders as well. We can do third order, we can do fourth order. This is called successive differentiation. So over here many people actually ask, what is this form of writing this second order derivative? We write third order as d3y dx cube. What is this? Is it actually cube or not? So it's basically just a way to write this particular differentiation order, right? It's nothing to do with cube and anything else. So don't just get confused. And also we saw that dy by dx equals to 1 by dx by dy. We saw that and we used that, and we kind of intuitively got the idea because it comes from d delta y by delta x. Applying by limit applying, we get this to this, right? And that's why we can do the opposite over here, because it's linear. Otherwise, in case of higher order derivatives, it's not linear. So we cannot really write as d2y by dx square as d2x by dy square. These are not same. So just make sure that whenever you are doing questions of successive differentiation, don't try to do this in case you want to find the opposite of that. Inverse of that, sorry, not opposite, right? So these are the few key points of successive differentiation. I think we haven't been asked a question about this topic in PGDBA. So this is just to give in highlight how to do successive differentiation and what are these points you need to be cautioned about in case of examination. So that just one point of higher order derivative. That is the only point you need to be cautioned about. Otherwise, it's fairly simple. You just have to differentiate it repeatedly and nothing else. So today's lecture was till here only, and we have completed methods of differentiation completely. And from tomorrow onwards, we'll be starting with application of derivatives. So probably we'll be taking 5 to 6 lectures in AOD, and after that we'll be starting integral calculus. I also have planned to do coordinate geometry side by side, because that is a different topic and that doesn't really need any kind of correlation with calculus itself. So I'll be starting with straight lines and circles maybe in a week or so, right? So we'll be doing it along with the calculus part. So let's catch up tomorrow. Thanks for watching.